fitting that we have Robin Hudson giving the first talk here, given his amazing and remarkable contributions to quantum open systems, and in particular the development of quantum stochastic calculus, which you're going to hear about. Nowadays, I think due to some propaganda by Matt and myself and some other people like Hideo Mabuchi, this is generally referred to as the SLH formalism. But I think it's proper to hear from Robin, who actually developed this with Papasurati in the mid-80s. So this is really where it all started with, as far as quantum stochastic analysis. So it's a great pleasure to welcome Robin to give us the first talk of the program. Okay, Robin.
Okay. Well, I would like to thank the organizers of this splendid event. I was thinking it is not quite 20 years since I was last at the Newton Institute, and we did have in 1995, when Parthasarathi was the Hardy lecturer and quantum stochastic calculus was riding quite high, we did actually aspire to a one-day meeting here in Cambridge, and to have the luxury of a three-week meeting is really quite splendid, and I'm very impressed and very grateful to be here. So I think my job is to just talk about the sort of mathematics behind quantum stochastic calculus. I don't know all that much about recent physical developments, and I'm very intrigued to hear about them in the course of this meeting. So I'm going to talk about quantum stochastic calculus, but before that I'll say a little bit about quantum probability in general. Quantum probability is a generalization of the classical theory of probability, which is made necessary by the non-commutative multiplication of quantum observables. These are usually self-adjoint operators in a Hilbert space. For example, everybody knows the momentum and the position observables P and Q satisfy the Heisenberg commutation relation. Here, Planck's constant, I'm afraid H has too many roles in this talk, but this is the first one. It's Planck's constant, and Planck's constant, I just remind you, probably don't need to as you're all physicists, but Planck's constant is very, very small in everyday units. We, in quantum probability, at least some of us, find it convenient to set it not equal to 1, but equal to 2, at least the non-normalized one, the normalized one, I'm sorry, and that means that the Heisenberg relation reduces to PQ is minus 2i. The 2 is probably very irritating for some people, but it gives you a much better tie-up between physics and probability with its normalizations if you have that 2 there. So because things don't commute, some of the things that one would expect in a theory of probability don't work. For example, one thing that doesn't always work is the idea of a joint probability distribution for example, the pair P and Q, which don't commute with each other. You might try to define this by saying that essentially its Fourier transform would be the quantum characteristic function of joint characteristic function of P and Q. In other words, this is a well-defined unitary operator, so you can form its expectation, and then you can say if some rho has that as its Fourier transform, if this identity holds, then that rho should be the joint probability distribution for P and Q. And if you do that, well, sometimes it works very nicely because you get a very nice joint Gaussian distribution. By the way, this would look much more messy with quarters and funny things happening there if I hadn't taken H equal to 2. But you get this nice joint Gaussian distribution if you're in the ground state of the harmonic oscillator. But if you're in the first excited state, you find instead something that looks not too bad. You just have this polynomial sticking in front of your Gaussian factor, but then that if you look carefully at it, you're going to be in trouble if you start calculating the probability, for example, that the pair PQ lies inside the unit circle. Of course, you will be violating the Heisenberg uncertainty principle if you ask for such a probability, and the truth is you get a silly answer, namely a negative one, with what seems to be quite a reasonable definition of a joint probability distribution. So joint probability distributions don't always exist. Another thing that doesn't always work is the notion of conditional expectation and the associated probabilistic concept of a martingale. Well, I want to talk about quantum forms of Brownian motion and sort of leading up to that to see where it comes from. I want to start not with a single degree of freedom, P and Q, but for many degrees of freedom. Let's suppose we've got these things satisfying the standard Heisenberg commutation relations for many degrees of freedom. And then let's do the following rather strange thing. Let's form the sum of the first n of the p's and the sum of the first n of the q's, and then divide this one by root n and this one by root n, and take that commutator. And if you do, you get a lot of nice cross cancellations, and eventually you get the sum of n commutators of pj with qj, but that's divided by root n twice, so you just get minus 2i, exactly the same as we started with. And if you know the central limit theorem in probability theory, you might therefore expect that in some sense this canonical pair, because that's what it is by this commutation relation, converges as n tends to infinity to a Gaussian limit. That's essentially what the classical central limit theorem tells you happens. But what can we mean by the conditions of independent, identically distributed, zero means and whatnot? And for that matter, what can we mean by convergence in distribution if we've just seen that canonical pairs don't have a joint probability distribution? And the answer to that question lies in what are nowadays careful to call the Stone-von Neumann theorem. It isn't only von Neumann's uniqueness theorem, as I used to think. It is actually as much due to Stone as von Neumann, that there is, up to unitary equivalence, exactly one irreducible representation of the canonical commutation relations for any finite number of degrees of freedom. And a consequence of that, it's a little bit indirect, and you may not be able to see it directly if you're familiar with the von Neumann theorem, but a consequence is that if you take your unique irreducible representation, you can pick it as you wish. Schrödinger representation is most people's favorite, where P is minus ID by dx and Q is multiplied by x. But if you have another favorite, that'll do just as well. And call that Hilbert space H0, then if you start with an arbitrary canonical pair in an arbitrary Hilbert space in an arbitrary state, then corresponding to that setup of P, Q, H and the state, there is a unique unit vector in not the Hilbert space where the representation lives, but the tensor product of that with its dual, which has the property of being invariant under the flip. That's the map that's from H0 to H0 dual that exchanges product vectors in that fashion, which has the property that, if you like, the characteristic function, I think there's oh, I see what's happened. Yes, that Q0's become a 9, hasn't it? Apart from that, it's okay. So the expectation is given by this vector here, living in a sort of standard Hilbert space. And that's going to be the same for all canonical pairs. So, for example, it will make sense to talk about convergence in distribution, because these vectors are all going to live in the same Hilbert space, so they can converge. So two canonical pairs are identically distributed if they have the same distribution vector, and a sequence of canonical pairs converges in distribution if the sequence of distribution vectors converges in the usual Hilbert space sense. What about independence? We want these canonical pairs to be in some sense independent. Well, we first have to define the joint distribution vector for two canonical pairs, and that uses just the two-dimensional form of the Stone-von-Neumann theorem. And in fact, the joint distribution will, if they're going to be independent, then the joint distribution just has to factorize into a tensor product vector like that, more or less what you would expect. Technical definition, zero mean and variance sigma squared. Well, zero mean just means zero mean. That's straightforward enough. The variance sigma squared, well, this is rather a cheat. You say that the pair P and Q both have variance sigma squared, if indeed they do, because there's the variance of P squared, bearing in mind that the mean of P is zero and it is sigma squared. But you've got to do something about PQ and QP, and you can't say that they're zero because they ain't. Their difference is definitely minus 2i, and the best way to resolve it is to say that. And finally, we say that a canonical pair that does have zero mean and variance sigma squared is Gaussian. Well, we need two different cases, really. We need to worry about what happens if sigma squared is 1, and in that case, what it means is that the distribution vector is just, well, if we're in the, we just take the harmonic oscillator ground state tensor with its dual vector. And if sigma squared is greater than 1, we take, this is probably a not very well disguised version of the thermal equilibrium state of the harmonic oscillator. You may be worried about two n's, but remember my p's and my q's are bigger than most physicists' p's and q's, and that's where that 2 comes in there, and we only see the odd integers coming rather than the usual harmonic oscillator energy levels. And so this is our state vector, and you may recognize it as a thermal equilibrium density matrix in disguise. When you think of density matrices, Hilbert-Schmidt operators in a Hilbert space H0 are really the same thing as vectors in H0 tensor, H0 dual. So that's when it's Gaussian. Nobody says what happens if sigma squared is less than 1, because you're all physicists and you know by Heisenberg sigma squared cannot be less than 1. That's what the Heisenberg inequality tells you. Seem to have lost a line. I wonder whether we can correct for that. No, I'm getting into big trouble because I'm yeah, well, the line that's missing at the top should say that just to observe that I defined what it meant to have zero means and variance sigma squared. But if you have an arbitrary canonical pair, as long as it has finite means and finite second moments, then you can always reduce it to 1 of variance sigma squared and zero means in the precise sense that I defined it by applying essentially an inhomogeneous linear transformation, canonical transformation. So you want the determinant alpha delta minus beta gamma here to be 1. So this is going to be a new canonical pair satisfying exactly the same commutation relation as you first started with. And then, if you have a sequence, now these terms make sense, of independent, identically distributed canonical pairs, of zero means and finite variance. Then if you look at the p's on their own, they are indeed mutually commuting observables. They are identically distributed, they are independent, they have zero means, and they do actually have variance sigma squared. You may remember on the previous slide there was this coth beta over 4 is sigma squared, and that actually works out right to give you the correct variance on P on its own. And therefore, by the classical central limit theorem, you would expect that this observable converges to a normal Gaussian limit distribution, and similarly for Q, the Q's, and in fact the joint quantum central limit theorem is completely consistent with that. It does agree with that statement. But in probability theory, one goes much beyond the central limit theorem in Donska's invariance principle, which says that you can construct Brownian motion. I think most people know that you can construct Brownian motion from random walks, but actually you can construct Brownian motion from a generalized random walk where each step isn't necessarily plus or minus 1 distributed, but can have an arbitrary distribution with the right mean and variance. And if you now do the way in which you approximate, well, for example, the aboriginal theorem is where you approximate the Gaussian by a random walk, but if you want to do a process version, you have to introduce this square root of nt. This, of course, means the integer part of nt, and you construct a process, a family of self-adjoint operators depending on time t by this sort of construction. That's going to converge to a Brownian motion of variance sigma squared. This is, of course, a Brownian motion in the probabilist sense, which is probably not a very good Brownian motion from a physical point of view. It doesn't have a velocity, for example. But anyway, that's what we mean by a Brownian motion for the purposes of this talk. And similarly, the Q's will give you another Brownian motion, also of variance sigma squared.
Are we allowed to ask questions?
Yeah, sure, sure. Please
so,
do.
Like, could you please clarify what operationally, what does it mean to define, to get a process out of a sum of canonical variables? So what are we do? Are we just measuring them?
I think probably the best answer to that is if I can draw a picture on the blackboard. What is this PN thing? What's actually happening? You do something like this. Let's mark off the steps of length 1 along the x-axis like that. And over the point 1, let's erect something like that, a P1, which is the first of our sequence. Then over the second one, let's erect P1 plus P2, and let's always divide these things by the same normalization root n, like that. So perhaps the third one might be down here. And so on. And then let's turn that sequence of dots into a random function simply by linear interpolation. So I draw a straight line like that, and a straight line like that, and so on. And I'm going to get a wavy, jagged line, and as n tends to infinity, that gives you the familiar picture of Brownian motion looking like that. By the way, please do feel, all of you, free to interrupt. It's always very satisfying to get plenty of questions during the talk. So we are going to have apparently two different Brownian motions, but the interesting thing about them is that they don't commute with each other, because if you look at the commutator of how I defined Pn and Qn, perhaps at different times S and T, you can see that there's going to be a sort of principal part, which is the sum at the beginning, which is going to just boil down to this quantity. It's going to be the integer part of n, lesser of S and T, divided by n, which evidently converges to S lesser t as n tends to infinity, plus some junk at the end. But the junk at the end, what's on top here is less than 1, because these are the fractional part of ns and the fractional part of nt, and we are dividing by n. So what the junk at the end has a 1 over n factor, so it's going to disappear. And we expect that the limit Brownian motions will satisfy this commutation relation. Now, how should we find two Brownian motions in that curious non-commuting relation like that? And to find them, excuse me if I sit down, we're going to have to consider again separately the cases sigma is equal to 1, and then when sigma is greater than 1. So let's start with sigma equal to 1, and we have to introduce Fock space, or the Fock space. Well, initially I want it to be over an arbitrary Hilbert space, and physicists usually think of Fock space, well, this is perhaps technically it's the boson Fock space. If you want to know about fermion Fock space from the point of view of quantum stochastic calculus, it's one and the same thing. It doesn't make any difference whether you're bosonic or fermionic. But let's define the Fock space first, the way that probably most of you are familiar with. You start with the vacuum, and then you form the direct sum of the one particle space, the two particle space, which is the symmetric tensor product of two copies of the one particle space, and so on. But from the point of view of quantum stochastic calculus, it's better to use a different definition of one and the same Fock space, which is to say that it's actually a Hilbert space that is generated by a family of special vectors called exponential vectors. And these exponential vectors, EF, there's one for each F belonging to the Hilbert space we first started with, the one particle space. And they have a special property, namely that the inner product of two exponential vectors is the exponential of the inner product of the labels of the vectors back in H. Now, you can argue using positive definite kernels and so on that there really is such a Hilbert space with these wonderful properties, and you can argue also that it's essentially unique in the sense that any two candidates, there will be a unique and canonical isomorphism from one to the other. And indeed, here is a candidate, the usual physicist definition of Fock space. In that case, the exponential vector is, you see, you just take 1 in the vacuum, direct sum f, and then you take f cross f, not over over 2 factorial, but to get the inner product to come out right, the square root of 2 factorial. Of course, with other conventions as to how you would define this direct sum, maybe you put factors in these terms here, then you may be able to get rid of the square root there, which looks a little bit ugly. But anyway, this convention will do for us. And one reason why this second definition is very useful for us is that it makes very clear the exponential property of Fock spaces, that there is a natural isomorphism allowing us to identify the Fock space over a direct sum down here with the tensor product of the Fock spaces over the summands, namely the exponential vector for a vector that is the direct sum of those two components is the tensor product of the exponential vectors there. So Fock space is more usefully defined in that second way than the first for our purposes. We're going to be principally interested in the Fock space over L2 of R, or R plus, the L2 space of the real line. And you can see because L2 of R has a natural family of direct sum decompositions, the corresponding Fock space, because of this property here, is in a natural, no, I shouldn't, let's get back to, oh, that's back, isn't it? Yes, where have we got to? Because L2 of R has a natural direct sum structure here, where you just go up to T and then after T, the corresponding Fock space has a natural tensor product structure. You can do that for any time T, so it's a continuous tensor product. And that's really basically what lies at the bottom of all stochastic calculus, all theory of processes with independent increments. Really a vast area of probability theory is really descended from this continuous tensor product structure. Okay. I'm not quite sure. It's a little disconcerting having lost the opening line of each slide, but how do we construct P and Q Brownian motions satisfying that commutation relation up there? Remember, that's what we're trying to do, and we're assuming that sigma squared is equal to 1 for the moment. Well, we introduce the mutually adjoint creation and annihilation processes. These are families of creation and annihilation operators in the usual sense, but I don't define them the way physicists usually would. I say what they do to exponential vectors, because that's going to be rather revealing. And the creation operator, which is the worse of the two, more complicated, is a parametric differentiation. This chi0t is the indicator function from 0 up to time t. So this is 1 between 0 and t, and it's 0 anywhere else on the real line. And so I add z times that thing to f, and then I differentiate the resulting exponential vector. You can show that these things depend in a nice analytic way on whatever is inside here, so the derivative really does exist. It should say, by the way, at z equals 0. This isn't, you don't do that. It shouldn't depend on z. You get rid of the z by putting z equal to 0. That's missed out from the slide. I'm sorry about that. And the annihilation operator, which you would like to be adjoint to it, and it certainly is easier. It's just saying that E of f is actually an eigenvector, and the eigenvalue is this inner product of that same indicator function with the vector f. And then you can check that the usual, the following commutation relations hold. All the A daggers commute, all the A's commute, and if you have an annihilation with a creation, then you get the lesser of S and T like that. Since these are unbounded operators, and I've only defined them on the exponential vectors, I can't strictly talk about their products as you would have in a commutator, and one avoids doing that by, for example, when you wanted to talk about AS commutator A dagger T, you switch the first AS over to the left of the inner product where it becomes an A dagger S, and here's the same thing the other way around. This is what's gone wrong? I think I've probably written the wrong thing there. I think it probably should say AT, AS, not AS, AT there. And then it's that thing that is equal to the lesser of S and T times the inner product EF and e.g. So you can avoid sort of mathematical technicality. You can avoid having to multiply unbounded operators, which mathematicians don't much like doing. And then if you define P and Q essentially by saying that Q is like the real part and P is like the imaginary part of the creation and annihilation operators, well, you get the right commutation relations, but you find that they are actually Brownian motions. And they are Brownian motions in the following precise sense. The P's can be simultaneously diagonalized in such a way that each one is like multiplication by a Brownian motion. So the formal theorem is that there is going, if you take the way you standardly realize Brownian motion on this Venus space, then there is a diagonalizing unitary operator from the Fock space to this L2 space of this probability space here, which has the property, first of all, that it maps the vacuum vector E0. I didn't point out that E0 is the Fock vacuum vector, to the function that is identically equal to 1. And more important, if you transfer, using this unitary operator, the momentum Brownian motion at time t onto an operator in the L2 of omega fp, you get multiplication by Brownian motion at time t. So it's like simultaneous diagonalization of a whole lot of different observables, and in this case, these observables just become essentially multiplication by Brownian motion, if you like, Brownian motion as sort of continuum eigenvalues down the diagonal. And exactly the same thing is true for Q. But P and Q don't commute. You can't diagonalize them simultaneously. The two diagonalizations must be different. They are not the same operator. And I just point out as an aside that although P and Q don't commute, it is possible to regard them as in some sense being independent, because if you look at, first of all, you can define this sort of self-adjoint operator. It's a completely rigorous object, and you can form e to the I of it, and you can look for the expectation of that quantity. And what you find is that for arbitrary xj, psj's, and yk's and qtk's, such an expectation always factorizes into the p bit times the q bit. And that's like being independent in classical probability. And that's a very nice property that the two quantum Brownian motions have, and in many ways very suggestive one, but I won't get seduced. Don't worry, John, I won't get seduced into talking about that. Well, that's what happens when sigma is equal to 1. When sigma is greater than 1, you have to write sigma squared is alpha squared plus beta squared, where alpha is essentially a cosh and beta is a shine, and take not the Fock space, but the tensor product of the Fock space with its own dual space, rather in the same spirit as when we were talking about the von Neumann theorem. And if you now define a new P, I'll call it P sigma, which is alpha times the old P in the first Fock space, tensor the identity, plus beta times the identity in Fock space, and then you take the dual operator P bar T in the dual Hilbert space. And similarly with the Q's, well, if you just look at that P, you can see, because you're in the Fock double vacuum vector, E0 tensor E0 bar, like that. If you're in that state, here's a Brownian motion for which this is the vacuum vector. Here's another Brownian motion for which this is the vacuum vector. and you've multiplied this one by alpha, so you've got a Brownian motion of variance alpha squared. You've multiplied that one by beta, so you've got a Brownian motion there of a variance beta squared. When you have independent Brownian motions of variance alpha squared and beta squared, and you add them, you get a variance, a Brownian motion again, and its variance is alpha squared plus beta squared, which is sigma squared, which is what we want. So P is the right thing, similarly Q is the right thing, and when you look at the commutator, essentially, because one of the two commutators is barred, you have to swap the square root of -1 that Heisenberg thought he knew to the square root of -1 that maybe it's the one that I thought I knew. And I can't say that it's the same one as his, but it's the opposite one to what these ones have. So you flip to the other square root of -1, and that's, you get this magic factor -2i coming. I'm not going to say much more about this Brownian motion, except to say that technically it's much easier to deal with because you have a cyclic separating vector. The double vacuum is separating for the von Neumann algebra generated by these things, as well as being cyclic, as it is in the Fock case. The Fock one is cyclic, but it isn't separating, and it makes the general theory of quantum stochastic calculus much easier in this finite variant, or variance greater than 1, sometimes called finite temperature. Essentially, if you remember, sigma was there was a Koth around, Koth beta over 4 is sigma, or something like that. It's a temperature state of the canonical commutation relations.
May I ask briefly
Yeah, sure.
about this particular trick, this doubling of space? So I'm kind of curious if this has a deeper role and convenience. Is there some physics behind it? Can I ask?
You're the physicist, so you'll have to produce the depth in that direction. But as a mathematician, I would say yes, it is very deep, because these von Neumann algebras are canonical examples of so-called type 3 factors. When von Neumann invented von Neumann algebras, he got these 3 types of factor. He only had one example of a type 3 factor. Much later on, using these kind of constructions, it was shown that there was a whole continuum of them. For different values of sigma, they're all non-equivalent to one another. They are mutually inequivalent.
Quickly. This is the Iraqi Woods decomposition or representation. If you think of the bosons as photons, one set of bosons stimulated, the other set would be the spontaneous photons. They're both photons, and they're not any different, but just in terms of the representations, that's what they'd be, because it's a thermal state you're trying to characterize here.
So, what about quantum stochastic calculus? Everybody knows Brownian motion is non-differentiable, and one intuitive reason is simply because xs minus xt is of order the square root of s minus t. So when you divide it by s minus t, you're likely to be in trouble as s approaches t. So that's an intuitive reason for it being not non-differentiable. But P and Q do show some hints of being perhaps not as undifferentiable as X is. And you can see it, for example, if you look at Q, which is A plus A dagger, and you look at the matrix element of Q between 2 exponential vectors, you get this nice formula here. And this object looks rather differentiable with respect to t by the fundamental theorem of calculus. Surely its derivative is just f bar t plus gt. We might worry a bit about whether f bar t really exists for an L2 vector, but it looks as though you ought to be able to define an operator dq dt in that way. Well, unfortunately, that doesn't quite work, because that doesn't define an operator. There is no such operator in the Hilbert space, but it does suggest that one should be able to introduce a theory of quantum stochastic integrals where wherever you see something like dA dagger, you convert it to dA dagger by ds at the end, and then you say dA dagger ds. Well, if I have exponential vectors on either side, I can shift the dA dagger by ds over to the left-hand side, and that will produce an f bar s. And similarly, this DAS will see the EG on the right-hand side and will produce a GS ds times that. And so you would expect that there should be such a theory of stochastic integration, but in order for that theory to exist, notice when I did that, I had to commute this dA dagger S through Fs to get it to the left-hand side of the inner product without F coming over to the left-hand side as well, which I don't want. And that means that the kind of process you would expect to be able to integrate does have to be adapted, meaning that it doesn't extend into the future at any time t. Ft only lives in the past of the Fock space at time t, like that. And such a theory works. And how does one set it up rigorously? Well, you start off with so-called simple processes, well, even more simple than simple, elementary processes, which are just processes which are just constant, then they take some non-zero value, and then they disappear again. They start off at zero. They're just a single block skyscraper function, but they're adapted processes. They are operator valued, and everybody agrees what the stochastic integral of such a thing should be, and you go from there. You go from simple to elementary. There's a technical mathematician's note that one can avoid multiplying unbounded operators, even though it seems you have to multiply them at that point. I won't label that. And then the first fundamental formula, so-called, is the following statement, that as long as the integrands are simple, which doesn't sound much a very big deal, certainly wouldn't enable you to solve interesting stochastic differential equations, but for simple processes you have this nice formula which essentially is just a rationalization of the idea that where you see dA dagger S, you replace it by dA dagger S ds, and then you take it over to the other side of the inner product where it becomes this F, but it's on the wrong side of the inner product, so it becomes F bar S at that point. And similarly, you deal with dA in the same way. This, there's nothing to say. You see HS. dTs is the same thing as ds, so it works directly. So that theorem is very easy to prove for simple processes, and where do we go from there? Well, we want to talk about products of two different stochastic integrals. There's still going to be only of these simple integrands, and very far from a practical theory for allowing you to solve SDEs and so on. But we want to talk about products of two, and the prototype to be aware of is the square of any old Brownian motion is, well, you can express this thing, first of all, it's the multiplying by itself a stochastic integral. So it's integral from 0 to t dx, and then you multiply that by another copy of integral 0 to t dx. And what you get is the sum of two iterated integrals. That's why this factor 2 comes from. First of all, the first one, then the second one, and then the second one, then the first one. The fact that they're both x means you can't see which is first and which is second, but perhaps x should have, you should think of two different x's which just happen to be the same thing there, plus this extra term, which I also write as a stochastic integral, although it seems unnecessarily heavyweight to do so, this strange Ito term. And these Ito terms are rather mysterious, but in classical Ito calculus, in quantum Ito calculus, which of course is going to turn out to be a generalization of classical theory, they emerge really as consequences of the natural commutation relations between annihilation and creation operators. Now, a technical thing, I've several times mentioned that we don't like multiplying unbounded operators very much, and to avoid multiplying by unbounded operators, what we tend to do is whenever we see two unbounded operators, we shift one of them to the other side of an inner product between exponential vectors, and then of course it becomes the adjoint, and all the processes that we consider have to have natural adjoints, so you can always adjoint them, at least on the exponential domain. And that will explain this otherwise rather horrendous looking statement that is the second fundamental formula, which tells us essentially how to multiply two stochastic integrals, m1, m2. Well, m1's gone over to the left, so perhaps it would be better to think of m, which is the adjoint of m1, times m prime, which is m2 on the right hand side, and it tells you what this inner product is, at least rather indirectly, because what you can see is that you've got something like the first fundamental formula for that one, but then you've got this m2s over on the right hand side, so nothing much has happened to that one. And here it's the other way around, nothing much has happened to m1, but you've got like the first fundamental formula for m2 plus this extra strange term, which perhaps you wouldn't expect. This is the Ito correction. But this theorem, which holds for arbitrary, at the moment for arbitrary simple processes, when you write it out, it is rather messy, but it's very, very simple in principle. It is just a consequence of the canonical commutation relation between creation and annihilation operators. Well, that wouldn't be all that interesting if it weren't for the fact that this second theorem, which really is the key to quantum stochastic calculus, enables you to go beyond these simple skyscraper integrands to the kind of thing that will come in solving a stochastic differential equation. Very often one expresses the second formula in this form up here that is like a generalization of Leibniz principle for differentiating a product, where you pick up this extra term dm times dm primed, and dm times dm primed is worked out for two linear combinations of dA dagger dA and dt, in which the coefficients are themselves processes. You work it out from the quantum Ito product formula, and in AA dagger language it's very simple. There's only one non-zero term, which is the one that violates Wick ordering, where dA comes to the left of dA dagger. If you go to the dp, dq, dt basis, then it looks a bit more complicated, but it's worth doing that because you can see that classical Brownian motion is enclosed in there, and quantum Brownian motion is enclosed in, miss out the IDT, but just look at dq, dq is dt. You've got another copy of classical Brownian motion, but of course P and Q don't commute, and the cross term dp, dq is either plus or minus IDT. Well, the point of that second formula, as I said, was that it allows you to extend to to the kind of integrand processes that you will meet when solving differential equations, and away from just skyscraper functions as your integrand. And the way to do it is to put the two sides on the second fundamental formula equal to one another, and then to cut the stories rather short, as I see a chairman menacing me over there, you get an estimate, of which this one for the creation integral is typical. You get an estimate that allows you to extend the integration process from simple f's to f's that are such that this kind of norm here is finite. Well, I point out very, very quickly that in the non-Fock finite temperature theory, everything is much simpler. It's actually much more like Ito's original theory, which is just based on a single isometry rather than this family of semi-norms. But everything is nice in the non-Fock case. Stochastic integrals are always martingales. If you take the conditional expectation of the 1 up to time t at some previous time in the Fock space decomposition, you get the stochastic integral up to time s, rather up to that previous time. And you can ask the question, which is a natural one in view of what you know about classical stochastic analysis, where essentially every, in inverted commas, martingale is a stochastic integral, whether the converse is true here. And if you ask that question, the answer very briefly is yes in the non-Fock case, in a very clean and elegant way. No, in the Fock case, there is a third fundamental martingale, which is this gauge process, the number process given in this formula. And this number process is often, I think, attributed to Bilavkin. Parther and I had it, but I think it's probably fair to say that Parther had it because he knew all about the representation of processes with independent increments in the Fock space continuous tensor product, and he knew that the Poisson process must be lurking there as well, and sure enough, it was. And you can produce the Poisson process in a natural way. And just notice this new process has a nice property similar to creation and annihilation processes when you look at the matrix element between exponential vectors, where they got f bar, here you got g, here you got f bar and g together. And if we threw in the time process as well, then you don't get either f bar or g, they're both absent. So the four possibilities are all there. Okay. Oh yes, this is the Poisson process. I'm suffering from not being able to read the top line of my slide. What about unitary processes? Well, you can solve stochastic differential equations. You think of them as integral equations. When you do so, you can apply the iterative technique for solving differential equations, and you express your solution as the limit of a sum of, well, you have an operator in the initial space where the physics is, and then you have such an iterated stochastic integral like that. And using the fundamental estimate, as long as these operators here are bounded, then you can indeed show that there is always a unique solution, and similarly, I've written the equation with the driving term on the right. Physicists often prefer it to be on the left, the more like the Schrödinger equation. You can do the same thing there. Now what's happened? I've probably gone back by mistake. You can do the same thing on the left, and the difference between the two, notice, is here the EJs come in one order, here they come in the other order. And that's the only difference between left-driven and right-driven in this approximation process. And then you can ask the conditions for unitarity, and here they come. For well, it's a little bit complicated, but by using that Leibniz-Ito formula, this dmm prime is that, you get 4 conditions out for the 4 coefficients, which are written there, and these conditions are sufficient for u dagger is the identity, and another set of conditions are necessary for u dagger u is I. And that seems rather an unfortunate situation, but it turns out that if you use backward adapted quantum stochastic calculus, the 2 conditions exchange in that equivalence, and you find necessary and sufficient conditions for unitarity, and in the end you bring out the SLH formalism. I apologize for the fact that my H isn't the H it should be, but that's, I would say, where it comes from. Thanks for your patience. I'm sorry. Use my full time.
Despite all the pressuring, I think we actually have time for one more question. One more quick question.
Sorry, it was a bit of a rush at the end.
We don't know where Martin. Well, I don't know what a martingale is.
Aha, a martingale is essentially a fair game. If you imagine that you, or it's a betting strategy. If you go to a gambling house and you watch somebody tossing a coin, of course, nowadays gambling houses are a little more sophisticated, but that's the principle. You can imagine that just watching this guy endlessly tossing the coin, and you take in the information of the sequence of heads and tails, and you devise a strategy. For example, if you see 3 successive heads, you'll bet on heads. A martingale is essentially a strategy for dealing with that. And the gambler's ruin idea that all gambling always leads to ruin is that you will never actually get rich in that way, because it is a martingale. Nothing will ever happen. Brownian motion is itself a martingale. It's equally likely at any point to go up as it is to go down. So you're not going to get rich by looking at the tendency of Brownian motion and hoping that it will continue, because it's not likely to.
So, in practice, you mentioned I'm a physicist, of course, so I use this in a physics context, but there's a number of elements of this formalism which are extremely useful, but then there's questions that start to arise associated with 2 different parts of the story. I'm kind of curious about them. One part is questions associated with the renormalization one expects in any coupled system, in the open system. So, if I do quantum Brownian motion, I have to be very careful about how I renormalize the bath based upon the system so that the system actually converges. And I'm kind of curious if there's any sort of renormalization physics that enters when you start to examine this and look at the back action that H in your language has on the stochastic fields.
Yeah, I'm probably less equipped to answer this question than, for example, John, but I would say this, that using these techniques, you can dilate to a unitary process any reasonable master type equation. And you actually get a unitary dilation, which is genuinely unitary process, and then when you take the vacuum expectation, you get back to where you started with. And you can do that in complete generality, modulo problems with bounded operators. Everything has to be bounded. You can't necessarily...
I guess to give you a test case, one would like to account for sort of one-dimensional equivalent of the Lamb shift, which is an effect from coupling to the vacuum.
Yeah, well, now you're getting beyond my pay grade. Yeah.
So that would be some of the test case. And then
Yeah.
second question has to do with environments where there's correlations.
Mm-hmm.
And so obviously there's a very deep and long theory and probability language about environments that are not martingales. And I'm kind of curious if there's any easy extensions of this type of relation to those.
Well, of course, Brownian motion is very nice because it's uncorrelated and it's very easy to deal with. There are, to a greater or lesser extent, variants of this sort of theory where you can have different kinds of quantum noises, and they can incorporate such correlations as you feel you can deal with. But of course, the further it gets from Brownian motion, the less easy it is to develop the theory completely rigorously, you know.
Okay, well, no further questions. I can thank the speaker again.